Okay, so now that we have this set up, set up in the way that we do, it's really easy to get it so that the gravity affects all of the movers. So this mover looks at the gravity is the force of gravity between all of the other movers is applied to this as is applied to every ball. So it's kind of exciting that we can do this, and so let's go ahead and delete our attractor mass, and we're going to take out the attractor, and so let's look at our code. Oh, I want to delete our attractor mass while we're at it. And I'm just going to hash this out for now and hash out our attractor right here. So how do we do that? We're going to make a nested for loop, and so for every mover we want to look at every other mover. So let's just consider M, the mover that we're looking at right now. We want to look at every other mover. So what we need to do is make another for loop, and we're going to just use, instead of enumerate, we're just going to use the index j. So for j in range length len of mlist, then we're going to we want to attract the mover that we're looking at right now, where we want to attract it to all the other movers. So we say that by doing mlist and put in j. And one thing that you want to notice here is that it will bug out because I and j we're looking through the same mover list twice. So if I and j are the same thing, our m is going to be equal to the mover that we pass in over here. So it's going to be, the mover is going to be attracting to itself, which doesn't make any sense. So we're going to put in a condition right here, and if I is not equal to j, then we want to do this, and I'm going to put some gobbledygook there because I remembered that we need to move down our number of movers. Let's try 5. If you have a large number of movers now, it's going to bug out and crash. So now let's get rid of the bug that I wrote in. Let's test it. And for j in range, we need a paren there, and expected indent block there. Completed successfully. So let's look at this. And right now we only have, about a half a second. And let's move this up a little bit. So 13 movers, 17 movers, it's taking 3 seconds. So it's taking quite a lot. This is really inefficient. But we're not going to be considered with that right now. We're just going to try that. So it's kind of exciting, and it's moving, and then eventually it just coalesces into one object. I don't know why it's doing that, and I don't know if that's something if you want to avoid, or if that's just gonna happen the way we have it set up. I don't know. I think that we can look at like some of our variables in here, and we could change them around to maybe that it doesn't coalesce as quickly, And the way I think we can do that is I think we can do, first of all, I think we could play around with these two variables, which I haven't considered yet. And then also I think we could change gravity and um, yeah, I guess we could give them larger masses or smaller masses or something, but let's not do that. Let's just make our universal constant of gravity weaker and test it. Oh, please don't bug out. Okay. So it seems like it's going it's not coalescing as quickly. Let's see, it coalesced, before our timer ran out at uh, around 230 uh, steps. So we know that it's not coalescing as quickly. So yeah, that's a pretty exciting little chunk of code, and that's going to conclude our force chapter, and we can use this setup in the future. And let's yeah, so it's exciting little chunk of code.